So I'm Pete. I'm a co-founder of a quantum computing startup, which means that I'm financially motivated to mislead about the state of quantum computing technology. Tens of thousands of years of human life, billions of dollars of capital, publicly traded companies whose stocks are crazily swinging up and down, world leaders like Jensen Huang, Bill Gates, and Martin Shkreli desperately trying to make sense of the endless headlines. It's pretty frustrating to feel the ship swinging between extreme pessimism to deranged optimism. If you ever really want to see a real quantum computer, at some point you have to reckon with pretty extreme engineering challenges. Despite that, about 8 years ago, myself and my co-founders moved here to Silicon Valley, and we started making claims that we are going to solve those challenges. This is where we're now testing thousands of wafers of quantum chips that are built in a commercial semiconductor fab where you'd normally build chips for laptops and cell phones. These wafers actually contain a superconducting material and single photon sources. Those chips are now becoming so complex that we're actually running out of cryogenic cooling power, and so we've introduced higher power systems. We do still use these chandeliers when we want to test just an individual chip, but I think we're all looking forward to putting these chandeliers on eBay. So we're really lucky now to have access to the LCLS2 cryo plant at the Stanford Linear Accelerator. This has about 36,000 watts of cooling power at 4 Kelvin. That's pretty much exactly the same scale as the systems that we're going to put into our sites in Australia and Chicago, where we're breaking ground in the next few months. And much like a conventional data center, where we have 19-inch cabinets, each containing hundreds of chips, our team has been really hard at work designing and commissioning this system. This is our cryogenic cabinet. So essentially we flow liquid helium into this system from the top, and that cools our chips to their operating temperature. And if I think about the history of the semiconductor industry, self-driving cars, rockets, robotics, and so many other technologies, to me it really doesn't look like a story about breakthroughs. It's a story about grind and about sustained and dogged progress over decades. It's about leveraging capabilities from adjacent fields, about desperately trying to keep things simple, and most of all, it's about taking something that everybody said was impossible, something that's been impossible for decades, something that's failed and failed and failed, and dragging it, kicking and screaming, over the threshold of usefulness. You can build 3-nanometer transistors. You can catch a rocket falling out of the sky. You can drive a car across a city with nobody behind the wheel. And it's really an extraordinary opportunity to find ourselves in this position where we have a serious shot at adding a real and useful quantum computer to that list.